Question number 11. Two parallel steel wires A and B are fixed to rigid support at the upper ends and subjected to the same load at the lower ends. The lengths of the wire are in the ratio 4:5 and the radii are in the ratio 4:3. The increase in the length of the wire A is 1 mm. Calculate the increase in the length of the wire B. Okay, so here see, according to this question, here we have two parallel steel wires. That means the Young modulus of wire A and Young modulus of wire B is same. So first we can write, that means y1 is equal to y2. Then these two wires are subjected to the same load. That means we can say, so F1 is equal to F2, that means forces are same. Then we are given the lengths of the wire in the ratio 4:5. So L1 is to L2 is equal to 4:5. Then the radii are in the ratio. So R1 is to R2 is equal to 4:3. And the increase in the length of the wire A is 1 mm. So we can write, that means delta L1 is 1 mm. And we have to find out the increase in the length of the wire B. So delta L2 is equal to what? Okay, so we are going to use the first expression, which is Young modulus of wire A and Young modulus of wire B, both are same. So we know Young modulus gives us stress upon strain relation. So here stress is F by A and strain is delta L by L. So here it would be F1 by A1 into L1 by delta L1 is equal to F2 by A2 L2 by delta L2. And we know that F1 and F2 both are same, so we can cancel out this 2. Then we'll be having, so delta L2 by delta L1 is equal to A1 by A2 into L2 by L1. So from here we can write, so delta L2 is equal to A1 by A2 into L2 by L1 into delta L1. And we know that cross-sectional area, which is A1 and A2, these two would be equal to pi R1 square by pi R2 square into L2 by L1 into delta L1. So pi will cancel out. Then we'll be having R1 square by R2 square. So according to this, R1 square is 4 square and R2 square is 3 square. Then L2 by L1. So we are given L1 is to L2. That means it would be 5 by 4. Then delta L1, which is 1 mm. So here it would be 16 by 9 into 5 by 4. So 4 4s are 16, which is 20 by 9. And after calculating this, we'll be getting 2.2 millimeter. So that is the answer. So the increase in length of the wire would be 2.2 millimeter. Question number 12. Two wires of equal cross section but one made of steel and the other copper are joined end to end. When the combination is kept under tension, the elongation in the two wires is found to be equal. Given Young's moduli of steel and copper are 2 into 10 to the power 11 Newton per meter square and 1.1 into 10 to the power 11 Newton per meter square. Find the ratio between the lengths of the steel and copper wires. Okay, so as you can see here we have two wires. One is made of steel and the other one is copper, and they have equal cross-sectional area. That means we can say, so A1 is equal to A2 is equal to, let's say, A. Okay, then so equal cross section, first we have equal cross sectional area, then it is kept under tension, so we can assume that the tension is also same. So F1 is equal to F2 is equal to F, and the elongation in the two wires is found to be equal. That means we can say that delta L1 is equal to delta L2. And given the Young's moduli of steel and copper, so Young modulus, let's say Yn is equal to 2 into 10 to the power 11 Newton per meter square, and Y2 is equal to 1.1 into 10 to the power 11 Newton per meter square. So we have to find out the ratio between the lengths of the steel and copper wires. So first we know that Young's modulus expression Y1 gives us stress upon strain. So it is F upon A L1 by delta L1, and Y2 is Young's modulus of copper, which is F upon A into L2 by delta L2. And if we take the ratio of this Y1 and Y2, we'll be having F by A dot L1 by delta L1 divided by F by A into L2 by delta L2. So this term F and A will cancel out. We'll be having L1 by delta L1 into delta L2 by L2. And we have to find out the ratio between the lengths of the steel and copper. So L1 by L2 is equal to Y1 by Y2 into delta L1 by delta L2. Oh, so here delta L1 and delta L2 is also equal to each other. So this will cancel out. So we have Y1 by Y2 only. So Y1 is 2 into 10 to the power 11 and Y2 is 1.1 into 10 to the power 11. So 10 to the power 11 will cancel out. We have 2 by 1.1, which is 20 by 11. So this is the ratio of L1 and L2, 20:11. So this is our answer here. Question number 13, it says a lift is tied with thick iron wires and its mass is 1000 kg. If the maximum acceleration of lift is 1.2 meter per second square and the maximum safe stress is 1.4 into 10 to the power 8 Newton per meter square, find the minimum diameter of the wire. Take G is equal to 9.8 meter per second square. Now here one word is mentioned, that is maximum safe stress. Now we have to remember one thing, that maximum stress in the wire will be when the lift is going upwards, okay, and that time the maximum tension F would be M into G plus A. Okay, so you have to remember about this thing, that when we are considering maximum safe stress, that means we are saying that the wire or the lift, basically the lift is going upwards, and that moment we are going to have the maximum tension as well. Okay, now in the given data G is mentioned, which is 9.8 meter per second square. Then the acceleration is mentioned, which is 1.2 meter per second square. Then stress is also given, that is 1.4 into 10 to the power 8 Newton per meter square. And here we are going to put the values, and mass is M is equal to 1000 kg. So 1000 into G is 9.8 plus 1.2 Newton, and it would be 11,000 Newton. Okay, now we know that stress is equal to force upon area, right? So force is 11,000 divided by area. Now for area we know that pi r square is the cross-sectional area, and we have to calculate the diameter basically. So from here only we can say that stress is equal to 11,000 divided by pi into d by 2 square, which is equal to 11,000 divided by pi d square into 4, and then d square is equal to into 4 divided by, we know, 3.14 into stress. So 11,000 into 4 divided by 3.14, and the value of stress is 1.4 into 10 to the power 8. And after calculating this, we'll be getting 10 to the power minus 4 meter. And that means D is equal to 10 to the power minus 2 meter, which is equal to 0.01 meter. So this is our answer. So the minimum diameter of the wire is 0.01 meter. Question number 14. The length of a metal wire is L1 when the tension in it is T1 and L2 when the tension in it is T2. Find the original length of the wire. Okay. So according to this question, we have to find out the original length of the wire. So let us suppose that we are assuming the original length is L. Original length is equal to L and cross-sectional area is A. Okay, that means when the metal wire is L1, that means we can say the change in length delta L1 is equal to L1 minus L, and change in length delta L2 would be L2 minus L. Now we know that Young's modulus is force stress upon strain, which is tension upon area into L by L1 minus L for the first case, which is equal to T2 by A L by L2 minus L. So we have to solve this equation, then we'll be getting, so A will cancel out with each other, L will cancel out. So we'll be having T1 into L2 minus L is equal to T2 into L1 minus L. Then T1 L2 minus T1 L is equal to T2 L1 minus T2 L. Then T2 L minus T1 L is equal to T2 L1 minus T1 L2. Then take L as common, so which is equal to T2 L1 minus T1 L2. So L would be T2 L1 minus T1 L2 divided by T2 minus T1. So this is our answer. So the original length of the wire is this. Question number 15. A metal bar of length L and area of cross-section A is rigidly clamped between two walls. The Young's modulus of the material is Y and the coefficient of linear expansion is alpha. The bar is heated so that its temperature is increased by delta T. Find the force exerted at the ends of the bar. Okay. So at first we know the expression of Young's modulus, which is equal to stress upon strain. That means F by A dot L by delta L. Now we have to find out the force exerted on the bar. Okay. So from this expression, F is equal to YA delta L divided by L, right? Now here it's mentioned that the coefficient of linear expansion is alpha when the bar is heated so that its temperature is increased by delta T. So these two are mentioned here, and we know that when solid gets heated up, it expands basically, and that expansion or that change in length delta L is equal to original length of that solid, or here it's a metal bar, so original length of that metal bar, which is L, then the increased temperature, which is delta T, and it's directly proportional to the alpha, right? So we have delta L is equal to L into delta T into alpha. So we have to put the value of delta L here, and we'll be getting YA into L delta T alpha divided by L. So L will cancel out, and we'll be getting YA alpha delta T. So this is the force exerted and the ends of the bar. So this is our answer.